Good afternoon. Today we're going to be discussing the disposal of radioactive waste in Tooele County, Utah. Myself, Jenna Faulkner, Jenessa Michael Freeman, and Tanner Jensen will be discussing the research and conclusions of Michael Freeman on this topic. There's national radioactive waste being deposited in Tooele, Utah, and this is an issue because the radioactive waste is continuing to dissipate, and the environment of the disposal site gives access of this radioactive material to the groundwater, which is obviously an issue. We propose depositing this nuclear waste using sub-seabed subduction methods to encapsulate this material inside the earth. We'll use concrete encased deposit vessels, and there are several aspects as to why this is the most viable option, but cost is one of the most overwhelming differences between this and other competing methods.
Nuclear waste is created naturally at nuclear energy facilities as well as medical waste. That waste is then classified as high or low level radioactive waste. Currently, there are 5,408 drums of this high level radioactive waste from the Cold War era stored at the Clive facility in Tooele County, Utah. The Clive facility treats this waste that can include everything from the clothes the workers were wearing while working at the facility to actual concrete and steel pieces of the facility itself. This waste is shipped by rail and by truck to the Clive facility and is then treated with chemical processes to attempt to make it more stable. The goal here is to minimize contamination, since this radioactive waste is harmful not only to the environment, but to humans and animals as well. The waste is deposited in embankments and cells to attempt to encapsulate it and keep it contained. These cells and embankments are constantly monitored to check for breaches of air and water that could contaminate the environment around them. The problem with the Clive facility is that it's not intended to be permanent. It's a temporary solution. Originally, 15,600 vessels of radioactive waste were proposed to be stored at the site, but Utah's governor objected and the number was limited to 5,408. There's much more radioactive waste than that in our environment naturally today, with a 2010 audit by the U.S. Department of Energy stating that 10,192 drums are currently being held at a secretive classified interim site awaiting permanent disposal. Clearly, the Clive facility is not the right place to do this, since it has already been limited and has other distinct disadvantages.
There are two main problems with radioactive waste storage at the Clive facility. The first is continual growth. Over time, radioactive waste doesn't dissipate. It simply becomes more radioactive and dangerous. The increased radioactivity corrodes the steel container holding the material and makes it more toxic and more harmful to people. The second problem is geological location. The proper location for this radioactive waste is deep in a geological environment away from all bodies of water. However, the Clive facility is located in a dried up lake bed of Lake Bonneville. This area is previously corroded from the lake and additionally corroded from the radioactivity. Therefore, possible flooding that occurs over the salt flats can cause the radiation to leak out and contaminate the local community. As radiation seeps into the surrounding environment, it can make the surrounding material corrosive, flammable, or chemically harmful. As discussed in the 1994 Utah Environmental Summit, these contaminations can be spread by contaminated drinking water, plants, soil, dust, or fumes from landfill seepage into groundwater, or air emissions coming from debris or incinerator smokestacks.
After analyzing different dispositive methods to dispose of the radioactive waste, it was concluded that using the sub-seabed subduction zone is a more viable method compared to other methods of disposal on land, like the rock melting method. The main point of this method is to deposit the radioactive waste where two tectonic plates meet. One of these plates is going to be going underneath the other one, roughly around 2.1 centimeters annually. Thus, once the waste is deposited at this location, it will sink down into this tectonic plate and slowly move down, thus providing a perfect a permanent method to dispose of this radioactive waste. Once the waste is brought to one of these trenches, it can be dropped off by a barge. Then, because of the design of these vessels, it will go down through the water at roughly around 50 miles an hour and embed itself into the clay sediment at the ocean floor. If one of these vessels was to implode and explode all the radioactive waste once it hits the bottom, this clay has properties that actually traps the radionuclides. If these radionuclides were to disperse into the surrounding environment, this clay would only allow it to go at about 1 millimeter annually. As such, compared to the 2.1 centimeters as the plates are going down, this is trivial and will not make any difference at all. These deposit vessels will be designed in a way that is very similar to a warhead or a projectile vessel. As such, when they fall through the water, they'll be able to gain high speeds and penetrate deep into the ocean. As shown, these vessels are divided into three main pieces. You have the nuclear fuel itself, which is surrounded by concrete and then encased in a stainless steel canister. This stainless steel not only adds weight to the vessel itself, but it also provides a barrier against the high alkaline pH that is at the bottom of the ocean in this clay. Thus, it will protect the vessel from outside corrosion. As compared to different methods, the cost for this method is relatively small. As shown, it costs about roughly $41,000 to create one vessel. Now this is minimal compared to the $225 million it costs to dispose of the waste through the rock melting method. Now this is for one vessel, which one vessel can only hold about 3 containers of waste, but even still, with 1,000 vessels needed to deposit all this waste, it would only cost about $75 million to complete. Now this is very small compared to the other prices. This is mainly due to the fact that the only cost is in the vessel itself. The geological location requires no extra construction needed. As such, it is very small compared to the others. This also creates a factor when talking about the risk associated with designing the location. There is no risk to design the location as it is already naturally made. Thus, this method is also safer to construct compared to the different methods that are out there. As such, disposal by the subseabed method is a more viable method to deposit the radioactive waste that is at Tooele County.
As Tanner and Jenessa discussed, there is a serious issue with the way radioactive material is being handled and deposited in Tooele County, Utah. After analyzing methods of deposit both on sea and on land, we have decided that the sub-seabed disposal method is the most viable option. This is considering the long-term effects of the radioactive spread, the efficiency of the actual deposit of the materials, the safety concerns to both the environment and the work crews, and the cost of disposal methods. We hope that this research will contribute to aid the problems arising in Tooele County from radioactive waste.